Good evening. Good evening, Jagdish. Good evening, Sachin.
Good evening.
Good evening, Aman. Is my audio clear? Audio clear, eh?
Yes, sir.
Yes, sir.
All right. ओके बाय द वे संडे को मैकेनिक्स का टेस्ट होगा, ठीक है? द लास्ट क्लास टेस्ट. गुड इवनिंग नीतू. Earlier Dr. Raj was saying that he wanted to take a test of MP on this Sunday, but वो पोस्टपोन हो गया अप टू नेक्स्ट संडे. सो MP का जो टेस्ट होगा वो नेक्स्ट टू नेक्स्ट संडे होगा. और द कमिंग संडे you'll have two tests, one of electricity magnetism and one of mechanics. तो मैकेनिक्स में ये जो फ्लूइड डायनेमिक्स आई विल बी टीचिंग, सेंट्रल फोर्सेस डिस्कस किया, उससे पहले मोमेंट ऑफ इनर्शिया, टेंसर एंड ऑल्सो लिटिल बिट ऑफ रोटेशन. ठीक है, आई नो दैट रोटेशन इज़ अ डिफिकल्ट टॉपिक, सो आई डिड अ टेस्ट लास्ट टाइम ऑल्सो, बट आई विल इंक्लूड 1 or 2 questions फ्रॉम रोटेशन ऑल्सो. ठीक है, सो दिस विल बी द 3 टेस्ट इन मैकेनिक्स एंड लेटर विल हैव फुल लेंथ टेस्ट, वहाँ पे इंक्लूडेड होंगे मैकेनिक्स के क्वेश्चंस. All right, so a very small topic is left that we need to discuss before we can move ahead. Okay, and then we'll start with the next subject. Mechanics will be almost over, and that topic is fluid mechanics. Okay, there are some equations, some formulas, some concepts related to fluid mechanics that I'm going to discuss today, tomorrow. I'll try to wrap up in 2 classes. If needed more, I'll take extra class, no problem. But I'm going to discuss the concepts and the formulas associated with fluid dynamics or fluid mechanics. So one section of the mechanics was related to the trajectories and the mechanical formulation of point mass particle, and then we studied rigid bodies, which dealt with translation as well as rotation. Fluid mechanics is a little bit different because fluid mechanics does not deal with rigid bodies. It does not deal with objects that have some definite shape or size. It deals with a peculiar kind of matter. Okay, the matter that we were concerned with when dealing with mechanics most of the time was solid matter. You know, objects, balls, planets. All of these are solid objects. Objects that have some kind of a fixed position in space. Objects whose dimensions do not change during the nature of its trajectory. So these are all solid objects that can be approximated in certain cases by point mass objects, and in those situations where it cannot be approximated by point mass objects, we take into account its dimensions as rigid bodies. So most of these are solid objects. So there is another kind of matter whose mechanics or whose motion that we can study, that is fluid. Okay, so fluid is something whose motion, when it study the motion of the fluid, now in the mechanics that you use to study how various physical quantities associated with the fluid changes over its trajectory or its motion, and that entire body of knowledge is known as fluid mechanics. So fluid mechanics is extremely vast in itself, difficult also, because of the nature of the fluid itself is not that easy to study it. It's a little bit complicated compared to normal mechanics concerned with point mass objects, but all of that is not necessary for us. We are only interested in the basics, so I'll try to clear the basics and the most important concepts that is necessary from our perspective of what is given in the syllabus. So the first question is, what is a fluid? Anybody can tell what is a fluid?
Which can flow?
Fluid is something that can flow. Yeah, good. That's good. It's a kind of a matter that can flow. It doesn't have a fixed dimension, doesn't have fixed dimensions. By dimension, I mean, let's suppose shapes. Doesn't have a fixed shape, and it takes the shape of the container in which it is present and takes the shape of the container in which it is present. Now you see fluid motion all the time. जब आप किचन में जाते हैं, when you go to the kitchen and you open the tap, you see flow of water. All right. When you go to a near the bank of a river, you see water flowing on the surface of the river. If you go to a waterfall, you see water falling from a particular height. If you see a candle or a diya, the gases you can see climb up, you know. So fluid mechanics is everywhere. There are different kinds of fluids. So let me give you a little bit of a classification of various kinds of fluids, and then we'll study the theorems associated with different kinds of motion. So there are different kinds of fluids that can be distinguished based on the nature of the trajectories that they make. So all fluids are made up of particles, essentially atoms or molecules. So these atoms or molecules which makes up that fluid, they move essentially, and their motion collectively can be seen as the motion of the fluid. When water is moving on the surface of a river, these are H2O particles traveling along the surface. When honey is falling from a bottle, so whatever the components of the honey are, those particles are creating some trajectory. When smoke is climbing up in the air, whatever the smoke particles are, they are creating some sort of a trajectory. So we do not necessarily study the individual trajectories of individual particles, but we rather study the aggregate of the entire velocity vectors in that particular region created by these particles in the first place. All right. Now, based on this, we can divide the fluid flow into certain categories. So one very common fluid flow is known as streamlined or laminar flow. Streamline or laminar flow. Anybody knows what a laminar flow is?
Regular flow.
What do you mean by regular?
That's not turbulent.
ओके गुड गुड। थोड़ा सा और क्लियर, टर्बुलेंट नहीं है का मतलब क्या है?
सर ऐसा मतलब दिखता है कि पाउच्ड है,
पाउच मतलब?
लाइक उसकी सॉलिड की तरह, मतलब एक पिक्चर
So the
ओवर टाइम।
different
चेन
layers of the
चेन नहीं
fluid
होता।
don't have relative motion between them.
दैट इज विस्कस एंड
And
नॉन विस्कस।
okay, sir, okay.
So streamline or laminar flow essentially means that if you look at fluid flow or fluid motion, and over a period of time you can trace out the trajectories of the particles that constitute the fluid flow, and these trajectories do not intersect with each other. Right. So the trajectories are not chaotic. So if the trajectories are not chaotic and these trajectories do not intersect with each other, but rather these trajectories are uniform for a particular fluid, then that's known as a streamlined flow or a laminar flow. So for example, so if there is some sort of a motion of a particular fluid body, a river or a pipe के through कुछ motion हो रहा है, and I can associate in that region individual particles that trace out different trajectories. Let's suppose like this. Okay, individual trajectories are going in some kind of a manner, and these individual trajectories do not intersect. All right, so these individual trajectories do not intersect. They are, as you can say, as uniform. They are not chaotic. In that situation, it is known as streamline or a laminar flow. Okay, so fluid flow is said to be streamlined or laminar if every fluid particle traces a definite curve or trajectory in space that do not intersect. For example, कभी कभी आप पाइप, आपके हाथ में अगर पाइप है और पाइप से पानी निकल रहा है, बहुत ज़्यादा फोर्स के साथ नहीं, धीरे धीरे निकल रहा है, तो जो पाइप से जो पानी निकलता है, अगर वो पाइप आप एकदम स्टैटिक होल्ड करेंगे तो आपको दिखेगा कि फॉर अ लिटिल वाइल द नेचर ऑफ द फ्लो ऑफ द वाटर इज़ वेरी यूनिफॉर्म इन द सेंस कि उसका जो शेप है वो भी यूनिफॉर्म है, ठीक, केओटिक नहीं है. यू कैन इनफैक्ट सी थ्रू इट. थोड़ी देर बाद वो केओटिक हो जाता है, उसमें डिस्टर्बेंसेज आ जाते हैं, टर्बुलेंसेज आ जाता है, लेकिन फॉर अ लिटिल वाइल यू कैन सी थ्रू इट. इट इज़ सो यूनिफॉर्म that in fact every single particle is tracing out some uniform trajectory or curve, and there is no chaotic motion due to intersections of those velocity vectors happening in that region. So that is a laminar flow or a streamlined flow, as opposed to a laminar flow or a streamlined flow. What is not laminar is what is known as turbulent flow. Okay, so turbulent flow का मतलब ये होता है कि the fluid is composed of motion, aggregate motion, where individual particles are tracing out trajectories that intersect at various points in space. Intersect का मतलब क्या है? If you have, let's suppose, one particle tracing out a trajectory like this, the other particle may, create some chaotic motion. There may be some sort of a vortex that is created in a particular region. The other particle may intersect with the other first particle's trajectory in a very short interval of time. There can be this kind of vortices which are created. So this is kind of a turbulent flow. Fluid particles do not trace definite curves in space, and motion is chaotic. So velocity vectors usually intersect, or trajectories usually intersect. Over a period of time, of course, over a short period of time. One very simple example of a laminar flow and a turbulent flow can be seen. अभी दिवाली के टाइम पे आप लोगों ने घर पे दिया या कैंडल तो लगाया होगा, है कि नहीं? लगाया था?
Yes.
Yes, sir.
तो जब दिया लगाते हैं या कैंडल लगाते हैं तो वहाँ से एक छोटा सा स्मोक निकलता है, वो दिखता है, वो विजिबल होता है, ठीक है. जब स्टार्टिंग में निकलता है वो स्मोक बहुत यूनिफॉर्म होता है, एकदम स्ट्रेट जाता है, बहुत ही स्मूथ फैशन में. थोड़ी देर बाद उसमें एकदम पूरा डिस्टर्बेंस आ जाता है. कभी नोटिस किया है?
Yes, sir.
Yes, sir.
Something like this, you see, something like this. ये बेसिकली इमेज एक अगरबत्ती का है. अगरबत्ती जो होता है, आपने अगर कभी जलाया हो घर पे या पेरेंट्स ने जलाया हो तो आपने नोटिस किया होगा कि अगरबत्ती से जो स्मोक निकलता है वो थोड़े टाइम के लिए बहुत स्मूथ होता है. इट्स वेरी स्मूथ फॉर अ लिटिल वाइल, and after some time there is a huge amount of disturbance that happens. So it is smooth because if you look at the nature of the trajectories initially क्या होता है कि for a small region the trajectories that is traced out by the particles are kind of streamlined or laminar essentially. मतलब the velocity vectors of these particles that are tracing out a trajectory in a given region over a period of time, they do not intersect. All right, so it's a very smooth sort of a flow that is happening here. You can see this. It's a very smooth sort of a flow that is happening, right? But after some time, यहाँ पे फिर chaotic motion आ जाता है. Velocity vectors start intersecting with each other, and then there is a very chaotic, unpredictable motion that happens. So this region is essentially the turbulent motion or turbulent flow, and ये जो region है starting का, ये जो region है that is laminar or streamline flow. इस तरह का मोशन आपको बहुत जगहों में मिलेगा. कभी पाइप से पानी निकल के आ रहा है, स्टार्टिंग में वो स्ट्रीमलाइन होगा, थोड़ी देर बाद वो टर्बुलेंट हो जाएगा. कोई टेप से पानी निकल के आ रहा है, किसी वाटरफॉल, किसी एक रिवर में भी आप देखेंगे कभी कभी क्या होता है, बहुत साफ पानी होता है, स्मूथली पानी फ्लो हो रहा होता है, बट फिर बीच में पत्थर आ जाते हैं तो फिर टर्बुलेंस क्रिएट हो जाता है, केओटिक एकदम फोमी टाइप का वो हो जाएगा. जब पत्थर नहीं होता, एकदम स्मूथ एक रीजन होता है, तो एक टर्बुलेंट फ्लो चलता रहता है. बट जब पत्थर आ जाएंगे दो तीन, फिर केओटिक मोशन हो जाएगा, फोमी वाइट कलर का हो जाएगा, वाटरफॉल टाइप का जैसा पानी होता है ना, सो एक टर्बुलेंट फ्लो क्रिएट हो जाएगा. सो दीज आर द टू काइंड्स ऑफ फ्लो वेयर वन इज द streamline flow and the other is the essentially the turbulent flow. All right, now let us discuss so this is essentially, we will be discussing mostly streamline flow only. Okay, turbulent flow हम बहुत ज़्यादा discuss नहीं करेंगे, it's a little bit difficult topic. So जो भी हम एक दो theorems बताएंगे, Bernoulli's theorem हो गया या फिर तुम्हारा Euler's equation हो गया, they are mostly for streamline flow only, and various questions will be related to streamline flow only, not for turbulent flow. Okay, let's move ahead to the next different kind of a flow. One is what is known as a steady flow. Okay, so we can classify various kinds of flow under different categories based on their properties. So based on whether or not the trajectories are uniform over a period of time or they are chaotic, we can divide it according to as laminar or turbulent flow. Now based on whether certain properties are fixed over a period of time or not, we can define what is known as steady flow. So steady flow का मतलब essentially ये होता है कि whenever some fluid motion is taking place, there are various physical quantities associated with the fluid motion. One of the physical quantities velocity, no doubt, but there are other physical quantities also like pressure हो गया हर एक point पे, temperature हो गया, density हो गया. So when these physical quantities do not change over a period of time as the flow is happening, then that's known as steady flow. So steady flow means the physical quantities associated with the fluid motion is constant with time. So you can say that it's a flow that is not a function of time. मतलब आप अगर सिस्टम को डिस्टर्ब नहीं करेंगे तो एट वन इंस्टेंट ऑफ टाइम जो भी फिजिकल क्वांटिटीज है, वेलोसिटी फील्ड जो है, प्रेशर फील्ड जो है, टेम्परेचर का फील्ड जो है, वही सेम क्वांटिटी आपको 5 सेकेंड बाद भी मिलेगा, एज लॉन्ग एज यू डू नॉट डिस्टर्ब द सिस्टम. So all the physical quantities associated with fluid flow like velocity, field, pressure, temperature, density, pressure, temperature, density, entropy, they do not change with time. Do not change with time. Do not change with time. So they may vary in space. Space में कोई variation हो सकता है. They may vary in space but not in time. but not in time. So for example, if there is some kind of a flow जहाँ पे there are two trajectories that are being created, okay, तो ये एक ऐसा flow है, let's suppose कि इस particular point पे there is a specific velocity of I say 4 meter per second, and इस specific point पे there is a specific velocity of 3 meter per second, इस specific point पे there is a velocity of 2 meter per second, whatever it is. So what is going to happen is that a particle is going to come and trace out this trajectory. Another particle is going to come and trace out this trajectory. Another particle is going to come and trace out this trajectory. And every particle, when it reaches here, will have a velocity of 4 meter per second. Okay, so essentially the velocity vector field in this region is a constant of time. मतलब ये जो trajectory है, ऐसा नहीं कि एक ही particle, only one particle went through this trajectory. This is a trajectory where individual particles are tracing out one after another. Okay, individual particles are tracing out this trajectory one after another, after another, after another. So every time a particle comes in that particular point, its velocity will be fixed with time. So that's a steady flow. And as opposed to steady flow, there is something what is non-steady flow. So what is non-steady flow? Which is not a steady flow. That means the various physical quantities are not fixed with time. Time के साथ change होता है. So once a particle traces out a trajectory, next particle comes, उसका इस point पे velocity अलग होगा compared to the previous particle. So that's a non-steady flow. Physical quantities associated with fluid flow. Vary with time. Okay, there are one or two more definitions associated with different kinds of fluid flow. One is what is known as incompressible fluid flow. ये तो मालूम होना चाहिए. What is an incompressible fluid flow? Incompressible क्या होता है?
Density is same throughout.
Density is same throughout space and time. Okay, so a fluid flow is called incompressible flow if the density of that fluid remains a constant with time as well as in the distribution in that space. So if density of the fluid remains constant in time in that region जब तक वो fluid flow हो रहा है. As opposed to this, you have compressible fluid flow. Compressible fluid flow is where density changes either over a region or with time. If density varies either in a region containing the fluid or with time. Okay, now final definitions. Viscous, जैसा one of you mentioned. So viscous flow and non-viscous flow. Viscous सुन के किस तरह का image आता है? Can anybody give me an example of a viscous liquid या viscous fluid?
Honey is more viscous than oil general.
Yeah, viscosity का मतलब होता है that when a fluid is flowing, then we can divide the entire region into various layers. So if there is some sort of a relative velocity between these layers, and as you go away from the source of that force or the pressure, then relative velocity, sort of the velocity, absolute velocity decreases, then we say that that fluid flow is viscous. And if the fluid flows in such a manner that there is no relative velocity between the various layers of the fluid, then that's known as a non-viscous flow. Okay, so for example, if I create a fluid flow with various layers, let's suppose, So as you can see, if there is some sort of fluid that is in motion, let's suppose this is a fluid in motion, then I can sort of separate the various regions of the fluid into separate layers, and these layers have some sort of a relative velocity between them, and the greater the relative velocity, greater is the viscosity of that kind of a fluid flow. Okay, so a fluid flow is said to be viscous if there is a viscous force between the adjacent layers of a fluid. For example, अगर आप देखेंगे the flow of ketchup, the flow of honey, the flow of lava, well, these are heavily viscous fluids, so they flow in such a manner that जो भी flow कर रहा होगा, अंदर का जो particle है, it will trace out a greater trajectory compared to a particle in the outskirts. So there will be relative velocity between the various particles tracing out different trajectories from the inner region of the fluid to the outer region of the fluid. Non-viscous is the exact opposite. In non-viscous flow, there is no viscous drag between the adjacent layers of a fluid. A viscous force. Between the adjacent layers. Okay, so you will see that all of them are moving at the same rate. All right, so these are different kinds of classifications of various kinds of flows that we have to deal with in various examples. Most of the time, we'll be dealing with some kind of a steady flow, steady laminar flow, where the physical quantities are remain constant at least in a particular point in time, and incompressible flows most of the time. In some situations, we may deal with viscous flows also. Okay, now this is by definitions based on just a general idea of how the nature of flow is taking place, but we can also define or separate them or categorize them based on some specific mathematical quantity, a physical quantity. So one of the common physical quantities to determine the nature of motion that is taking place is the velocity vector. But velocity vectors are usually for individual particles. So for a fluid, because it consists of many layers of many particles tracing out trajectories over a period of time, we do not deal with velocity vector of one particle, rather we deal with velocity field. Okay, so velocity field is these individual vector lines that can be drawn in a given region over a period of time. So we deal with velocity field, okay, or fluid velocity. So fluid velocity, so this is just a velocity field, a quantity that can summarize velocity vector field. Okay, just like you have electric field, just like you have magnetic field, that can be defined over a region over a period of time and not just for one individual particle or point. So this is a field. In certain books they refer to it as v, in certain books they refer to it as q, in certain books they refer to it as u. So u can be a function of the space coordinates xyz because it's defined in a given region, and time over a period of time. So u is the velocity field of a particular flow. Of course it can have various components in various directions. So if you want to represent u in terms of the x component, so the x component can be dependent upon x, y, z, t, I cap. Y component can also be dependent on the positions x, y, z, t, and z component can also be dependent on the x, y, z. Okay. Now, the earlier definitions that we talked about of various kinds of fluid flow, we can get some idea based on this physical quantity and how it behaves mathematically. So I'm going to give you a summary, a list of summary of the various kinds of motion that we will get based on the nature of this particular physical quantity. Some will derive later on, some is very much obvious. So kinds of fluid flow. So let's suppose that I'm interested in steady flow. Steady flow क्या था? What was steady flow, guys?
Velocity vectors don't change with time.
Time.
It is constant with respect to time. So whatever the velocity vector you create, vector field you create, a time derivative must give you 0. Okay, so if you have a particular fluid flow taking place and you have a velocity vector field associated with that flow, and the time derivative or the partial derivative, because u is a function of x, y, z, and t, comes out to be 0, it suggests that it is a steady flow. Okay. Number 2, incompressible flow. So incompressible flow is when the density is a constant. Density is a constant in time for a particular flow that is taking place. It is not obvious from this, but I'll derive it a little bit later on. You will see from the continuity equation that the you see the divergence of this, the divergence of the velocity field, if it is 0, then this suggests essentially that ek to ye tha for a steady flow and this is for an incompressible flow. This suggests that is equivalent. I will show it to you in just a moment how it is equivalent. Okay, is equivalent to density being a constant in time, being a constant in time. Okay. Now there are certain kinds of fluid motion in which there is no rotation taking place. There is certain kinds of fluid motion there is some sort of a rotation taking place. So it is known as irrotational flow if the curl of the velocity vector field comes out to be 0. So if the curl of the velocity vector field comes out to be 0, this is known as an irrotational flow. That means there is no rotational component associated with it in a given region. And as such, in such a situation, the velocity vector can be expressed as, or velocity field can be expressed as the gradient of some scalar function by the nature of all vector fields whose curl is 0, gradient of a scalar function. So I can say that u is the gradient of some scalar function, let's suppose phi, where phi is called velocity potential. It's called velocity potential. And if there is some sort of a rotational component associated with the motion, that is known as a rotational flow. rotational flow. Okay, and in rotational flow, the curl of the vector field, velocity vector field, is non-zero, and that quantity is essentially known as vorticity. Okay, so this quantity, which represents the curl of the velocity field, is known as vorticity. Okay, so these are essentially some very simple, obvious conclusions regarding the nature of the velocity field for different kinds of flow that takes place. All right, now let us go ahead to a couple of theorems that are associated with the motion. The first is a very simple theorem, which is known as the equation of continuity. Okay, so equation of continuity is something that you must have heard of in various different subjects. Also in electricity, magnetism, also you must have heard of equation of continuity. In quantum mechanics also you must have heard of equation of continuity. So whenever there is a conservation of physical quantity that happens over the transport of that physical quantity, then we get what is known as the equation of continuity. So if there is a transport of a physical quantity taking place which is subject to the conservation of certain physical quantity, we get what is known as the equation of continuity. So it's a very simple but an important uh, concept, equation of continuity. Now its derivation is slightly lengthy, so I'm not going to do it because it will take me around half an hour to derive it. I will only do the derivations which are slightly smaller. So the equation of continuity, if you are interested, you can take up any standard book. Even if you look up the net, you search in Wikipedia or maybe YouTube search, you will get the derivation for a general. So what it means is that if there is a specific region in which certain amount of mass is flowing in and certain amount of mass is flowing out, what equation of continuity says is the conservation of mass. That means the amount of mass that is flowing in a given amount of time is equal to the amount of mass that is flowing out. Okay, so whether you look at the pipe, the amount of mass that is flowing in over a period of time and the amount of mass that is flowing out over a period of time, that leads to equation of continuity. Or in general, if you construct a small cube in a fluid flow, and the amount of mass that is going in per unit time and the amount of mass that is going out per unit time, there is a conservation of mass associated with it, and from there we get what is known as the equation of continuity. You can look up the derivation anywhere in standard textbook. So that the derivation, the formula is essentially this. Okay, so the gradient, sorry, the divergence of, so del dot rho u plus d rho upon dt is equal to 0. Let me explain what the various quantities mean. You understand what del means. Okay, del क्या है आपको मालूम है. Del is I cap del upon del x, j cap del upon del y plus k cap del upon del z. So this is essentially a grad divergence. Rho is the fluid density. Okay, so this is true for both dense as incompressible as well as incompressible fluid. So this is fluid density. U is none other than the velocity field. Velocity field. Okay, so essentially, if let's suppose that there is some sort of a pipe in which water is flowing in and then there is water is flowing out. Okay, water is flowing in and water is flowing out. So the amount of water or fluid that flows in and the amount of fluid that flows out must be equal to conserve mass. Okay, otherwise the mass will not be conserved. So essentially the conservation of mass principle leads to, if you do a proper derivation, to this particular expression where the divergence of the density multiplied by the vector field plus the time rate of change of density is equal to 0. Okay, you'll have to memorize this, guys. You'll have to memorize this equation. Okay, it can be simply derived from the mass conservation principle. So continuity equation in physics is anything that talks about the transport of some physical quantity. In this situation, it talks about the transport of mass. Okay, mass of a fluid that is going from one region to another. So in fluid dynamics, in fluid mechanics, suppose The equation of continuity. Equation of continuity. The equation of continuity is the result of conservation of mass. The result of conservation of mass. So this is known as the differential form of the equation. Differential form. So this is a general equation, okay? The differential form of the equation. You can also have the integral form. The integral form लिख दूं क्या? एक second, let me write the integral form. Okay, so integral form also exists for the same equation. Integral form of the equation of continuity is rho u dot ds over a particular closed surface is equal to the time derivative of the integration of rho dv in that particular region. So this is the integral form. All right, now this is a general expression for the equation of continuity. For specific examples, like when fluid is flowing through a pipe, we can come up with a very simple expression. We don't even need to use this equation. I'll show you a simple derivation for anything that is traveling through a pipe, let's suppose. All right, so okay, let me use this diagram only. No, let's not use this diagram, थोड़ा बड़ा हो जाएगा. Okay, so let me use another diagram. So let's suppose that there is a pipe through which some kind of a fluid is flowing, okay? There's a pipe through which some sort of a fluid is traveling. Okay, so there are these specific trajectories that the particles are making. So if I look at the velocities, the areas of cross sections in the opening as well as in the exit. So let me draw a very small cross sectional volume. Let me take a cross section here, and let me take a cross section here. Okay, so if I take this particular cross section, थोड़ा सा मैं इसको वो कर देता हूँ, हाईलाइट कर देता हूँ. So if I take this cross section, and I take this cross section, or rather I take this cylinder, okay, an infinitesimal cylinder, and I say that the area of the entry is given by A1, the cross-sectional area of the entry where the fluid is flowing in is given by A1, the cross-sectional area of A2 where the fluid is exiting is given by A2, and the velocity is, let's suppose I say uniform at this particular point, and the velocity is given by V1 here as it enters, and the velocity is given by V2 here as it exits. And the cylinders, they have a dimension or length of around let's suppose del x1, and this has a length of around del x2. So the equation of continuity essentially says that the amount of mass that goes in at a particular interval of time and the amount of mass that comes in that same interval of time must be equal, okay? So it essentially comes from the conservation of mass principle. So applying the conservation of mass principle, what we get, that the amount of mass that is going in, let's suppose I call it del m1 in the exit, okay, so this is 1, okay, and then this is 2. Okay, so it is going in a given amount of time must be equal to the amount of mass that is coming in or coming out in a given interval of time. So in 1 second, let's suppose if 1 kg of mass is going in, 1 kg of mass must also come out in that interval of time. Or rather, the time interval does not necessarily have to be the same. I think the time interval does not necessarily have to be the same. I think time interval zaruri nahi hai. We take different time intervals. So what is mass? Mass is nothing but density multiplied by volume. So if I say that the density in cylinder, the small cylindrical element that I've taken is rho 1, and the volume is, let's suppose, V1 upon del T1. So this is equal to rho 2 and V2 upon del T2, or rather I call it del V बोल देता हूँ इसको, del V1 and del V2. So this is equal to rho 1. What is del V1? Del V1 is nothing but A1 del X1. Yes, A1 del X1 upon del T1. So this is equal to rho 2 A2 del X2 upon del T2. All right. So what is del X1? Del X1 is nothing but rho 1 A1. Del X1 is nothing but the velocity of the fluid over that interval of time, del T1 upon del T1 here, and this is nothing but A2, the velocity of the fluid as it is exiting the container over that interval of time that I took. Okay, del T2. So essentially this gives us an expression for rho 1 A1 V1 is equal to rho 2 A2 V. So this is the equation of continuity, the very simple expression for equation of continuity when some sort of a fluid is flowing through a regular tube or a pipe, right? This is a more general expression for some sort of fluid motion that is happening in three-dimensional space. And this is a very specific example of some kind of a motion that is happening through a pipe or a tube or something like that. All right. So where rho is nothing but a constant, so rho is nothing but the density, A is nothing but the area of cross section, V is nothing but the velocity of fluid at that cross section. We are talking about a streamline flow, okay, at that cross section. Okay, so therefore what we end up getting is IE rho A V is equal to constant of time. And this is true for all kinds of fluids, both compressible and incompressible fluid. If we take a very specific scenario, if fluid is incompressible, इसका मतलब क्या होगा? इक्वेशन में क्या फर्क पड़ेगा if fluid is incompressible?
तो constant.
Rho will constant.
Rho will be constant, it will not change. Okay, so incompressible means that rho is equal to a constant which is not going to change, and if it doesn't change, then IE, so we can say that AV is a constant, which simply means that A1 V1 is equal to A2 V2. So this is a very important formula that you must have seen in various situations. जब क्रॉस सेक्शनल एरिया ज़्यादा होता है तो वेलोसिटी कम होता है, और क्रॉस सेक्शनल एरिया जब कम होता है तो वेलोसिटी ज़्यादा होता है. कभी आपने गाड़ी साफ़ करने के टाइम पे या बाइक साफ़ करने के टाइम पे पाइप लेकर के गाड़ी में पानी मारा होगा, तो आप पाइप को दबा देते हैं. Did you notice? उसकी फ्लो को स्ट्रॉन्ग करने के लिए.
Yes, sir. When while watering the plants.
While watering the plants or cleaning your bike or your cycle or your car, जो पाइप होता है, अगर आप पाइप यूज़ करते हैं तो नॉर्मली पाइप जब खुला रहता है तो फ्लो बहुत धीरे आता है, लेकिन पाइप को जैसे आप टाइट कर देते हैं ताकि उसका क्रॉस सेक्शन एरिया कम हो जाए तो वेलोसिटी बहुत बढ़ जाता है. जितना छोटा हो जाएगा उतना ही वेलोसिटी उसका फास्ट हो जाता है. सो इट कम्स फ्रॉम द इक्वेशन ऑफ कॉन्टिन्यूटी. The greater the area of cross section, lesser is the velocity. The more the area of smaller is the area of cross section, greater is the velocity. So आप pipe को press कर देते हैं to close the gap to make it very small so that the velocity becomes very fast. It's a very strong flow. So it's something that you know by experience also, you know. Just a time. All right, let me give you a question related to this because questions have actually come. Question दूँ या मैं theoretical discussion को continue रखूँ? Let's continue the theoretical discussion. ना last में देखूँगा question. Okay. Okay, let me continue. Shall I continue the theoretical discussion?
Yeah, sure, sir.
Yes.
Okay. So yeah, so this is essentially the equation of continuity for a general sort of a motion of a fluid in three-dimensional space, and for a very specific situation where fluid is going in and out of some kind of a pipe or a tube or a cylinder or something like that. There are two more important concepts that we need to talk about. One is the equation of continuity, हमने discuss कर लिया. The other is the equation of motion associated with fluid flow. So when you talk about particles, you know, when you talk about point mass particles, we talk about Newton's second law. Newton's second law is very important because Newton's second law tells us that, you know, how the particle is going to accelerate, decelerate, whatever, in the presence of some force. There is an equivalent expression for fluids. In fluids, we don't talk about individual particles. We talk about the general whatever velocity field of that particular flow of fluid in some sort of a force field. Then the equation we talk about is the Euler's equation. It's known as the Euler's equation of motion. So let me do a very simple discussion and a derivation of the Euler's equation of motion. So Euler's equation of motion is when you apply the Newton's second law to fluid mechanics, the flow of fluid, then you end up getting a very specific equation which is very helpful in certain situations. So we'll derive that. It's not very difficult, it's quite easy actually. So let me take a very short derivation of this particular equation. Application of the Newton's second law to fluid flow. So we talk about Euler's equation of motion only for a steady flow. Okay, so we are only interested in steady flow here. So Euler's equation for a steady flow of an ideal liquid of an ideal fluid along a streamline is a relationship between velocity, pressure and density. मैंने बहुत डिटेल में प्रेशर वगैरह डिस्कस नहीं किया है. प्रेशर मीन्स फोर्स अपॉन एरिया, बट दे विल कम अप इन द इक्वेशंस. ओके, एंड डेंसिटी ऑफ मूविंग फ्लूइड्स. Okay, so let's look at the derivation. So if I take a particular streamline, okay, if I look at the fluid motion, if I look up the fluid motion and I consider a very specific streamline, one or two streamlines, let's suppose the streamline is something like this. Okay, let's suppose this is a streamline. Okay, it's going like this. Okay, it's going like this, and I want to look at in the presence of gravity. Okay, in the presence of gravity. I want to look at the pressure differences between 2 points in space. I want to look at the gravitational force that the particle is experiencing, and I want to create a force equation of motion for that particular particle, tracing out the trajectory. So to do that, what I'm going to do is I'm going to create some sort of a cylindrical volume element through which the streamline is passing through. Okay, it looks large, but it's a volume element. Okay, it's a cylindrical volume element having some kind of a height of I've taken it as ds. Okay, having a height of d small s. So its height is given as ds, and having an area of cross section. Let's say the area of cross section so it has an area of cross section of dA on both ends. Okay, dA on both ends. Now, because the flow of motion is happening, that means there is a pressure difference. If there is no pressure difference, there is not going to be any kind of a flow. There is a pressure difference between both ends, and it is the difference in the pressure that results in the fluid particle to go from one end to the other. So let's suppose that the pressure at the entry, let's suppose the pressure that is being created here, okay, I call it dP. Okay, I call it dP is the pressure here, and the pressure at this particular point P plus dP. So there is some kind of a change. It can be a positive change, a negative change, but there is some kind of a change in the pressure. So it's P plus dP. All right. So the fluid motion that is happening due to some sort of a force as a result of change in pressure. Okay. So force is pressure is what? Pressure is force upon unit area. So force upon area essentially. So that's pressure. So if I want to calculate the amount of force, then that is nothing but pressure multiplied by the area. So the amount of force that is acting on that streamline as it enters the volume element is dP dA, right? And the amount of force that is acting on the streamline as it exits the volume element is P plus dP into dA. This is clear? This is quite simple, right? Now, I also want to calculate the amount of mass that is contained in this entire body. So let's suppose that there is it contains some sort of a mass here. Mass in this area, in this element. So what is the amount of mass in the volume element? So the amount of mass in the volume element is what? It will be given by the density times the volume. Okay, so density times the volume. What is the volume? The volume is given by dA multiplied by ds. This is the mass of the volume element. Now, since I said that the whole thing happens in the presence of gravity, that means there is, apart from the force as a result of the pressure difference, there is also a force due to the gravitational attraction downwards. So that means there is a force that is acting downwards. All right. And that force is nothing but the mass of this volume element times g. Okay, this. And let me say that the angle that it makes with the fluid flow, this angle is nothing but theta. Okay, the angle is theta. So the direction of the gravitational force with respect to the fluid flow is the angle theta. Now, if I want to see what is the contribution of this kind of a force towards the fluid flow, then I'll have to resolve the force into two different components. So I can resolve the flow, either a force either in this direction in a direction parallel to the streamline flow or in the direction perpendicular to the streamline flow. Okay, so perpendicular to the streamline flow, the component of the gravitational force is mg sine theta. Okay, and parallel to the streamline flow, it's minus mg cos theta. मैं इसको सिर्फ mg cos theta ही लिख देता हूँ. mg cos theta is the is parallel to the streamline flow. Okay, so therefore, okay, now if I'm interested in writing the net force experienced by the particle, so let me say that the net force is how much? So net force is essentially the force as a result of the net force is essentially the force as a result of the pressure difference as well as the gravitation force. तो प्रेशर डिफरेंस के लिए आपके पास यहाँ पे क्या आएगा? प्रेशर डिफरेंस के लिए आपके पास यहाँ पे आएगा. सो इफ आई सेपरेट दिस आउट, डी पी डी ए माइनस पी डी ए माइनस डी पी डी ए, सो दिस इज इक्वल टू माइनस पी डी ए. तो प्रेशर डिफरेंस के लिए आपके पास आएगा यहाँ पे एक सेकेंड, ये डी पी नहीं है, आई एम सॉरी, दिस इज पी डी ए, राइट? मैंने यहाँ पे P लिखा, P लिखना चाहिए था, आई एम सॉरी. सो दिस मस्ट हैव बीन P. दिस इज द प्रेशर इन द एंट्री एंड द प्रेशर एट द एग्जिट इज P plus dP. Okay, some change in P, so I made a mistake there. So this should have been P dA minus P plus dP dA. So this is P dA minus P dA minus dP dA. dP dA नहीं, this is P dA only. हाँ, dP dA, सॉरी. सो यहाँ से मुझे मिलेगा PDA कैंसिल, माइनस DPDA आ जाएगा, माइनस DPDA. हाँ, this will be the force as a result of the change in pressure. So therefore, I will have minus DPDA, right? I'll have minus DPDA as a result of the change in pressure. Now, what is the contribution of the gravitational force? Will mg sine theta contribute to the motion of the streamline?
No.
No, sir.
No, because it is perpendicular to the motion of the streamline. The only contribution that will be coming from the mg cos theta term, but because the mg cos theta term is acting in a direction opposite to the flow of the streamline, therefore this will essentially become minus mg cos theta. Okay, all right, so now let's look at what cos theta is. Okay, let's look at what cos theta is. So if I say that because we're looking in terms of gravity, that the vertical distance, the vertical distance is given by dz. Yes, Said.
सर फ्लो अपवर्ड है तो मतलब ऊपर का प्रेशर कम होना चाहिए.
हाँ, तो ये इसलिए नेगेटिव में आ गया ना, माइनस साइन इंट्रोड्यूस हो गया ना इसमें.
ओके सर,
माइनस साइन इसलिए इंट्रोड्यूस हो गया यहाँ पे बिकॉज वो मैंने लिखा था प्लस, बट एसेंशियली इट शुड बी लेस. सो इफ आई लुक एट दिस पर्टिकुलर ट्राइंगल ऑफ ds dz and this is essentially nothing but the angle theta, then what is cos theta here? Cos theta कितना होगा?
dz by ds.
Z by ds.
dz by ds. So let me substitute this expression here. So this becomes minus dp dA minus mg dz upon, so m को भी मैं substitute कर देता हूँ. m is equal to rho dA ds g dz by ds. So therefore I essentially get this is equal to minus dp dA minus rho g dz dA. So this is a net force. So if I apply the Newton's second law now, Newton's second law क्या कहती है? It simply says that whatever the net force is going to result in some sort of an acceleration of that particular mass.
Sir?
Yeah.
So this dz is with respect to what?
dz is a vertical distance of a vertical height of the volume element.
With respect to the ground?
Reference can be anything, it doesn't matter. It's a vertical height So of course it's vertical, so we can say okay, but with reference to the ground, it will simply be some dz plus h, depending upon where the volume element is. I have not yet specified ground, so it doesn't matter. I am only interested in the vertical height of the volume element. So essentially, I am finding out the height of the volume element in the direction of gravitational force.
Okay, sir.
Okay, this gives us a clearer picture now, because every time we look at different fluid flow, ds is something that is indeterminate, but we will always know the change in height with respect to the gravitational strength vector. That is something vertical height हमें हमेशा मालूम होगा, बाकी separate cases में दूसरा height ds का तो कोई fixed थीटा नहीं है ना, तो इसलिए मैंने dz के terms में लिख दिया. Slowly I'll remove the s also. So if I apply Newton's second law, the F net is nothing but the mass times acceleration. So the F net is minus dp dA minus rho g dz dA is equal to mass is equal to rho dA ds. And what is acceleration? Acceleration is nothing but the velocity of the fluid with respect to time, that can be written as dv upon ds dot ds upon dt. Okay, so ds is nothing but the amount of distance that it has traveled in the particle in that streamline, the amount of distance it has traveled in a very infinitesimal time period. So therefore dv upon ds, so ds upon dt क्या होगा यहाँ पे, ds upon dt क्या होगा, v हो जाएगा. So dv dv ds. So if I write this d rho da ds, so here I write v dv upon ds. Okay, so here I will be able to cancel out ds, cancel out कर दिया मैंने. Now divide, let's divide the whole equation. Divide the equation by minus rho dA से मैं divide कर देता हूँ. So if I divide the entire equation by minus rho dA, this simply becomes minus rho dA हो गया तो dp upon rho हो जाएगा यहाँ पे, है ना, और यहाँ पे rho dA हट गया तो g dz हो गया, और यहाँ पे rho dA हट गया तो v minus v dv हो गया. So essentially this gives us this equation, dp upon rho plus g dz plus v dv is equal to 0. So the motion of a fluid in the presence of gravity and some pressure difference is associated with rho, which is the density of the fluid, okay, g, which is the acceleration due to gravity, dp, which is a change in pressure between 2 points, dz, which is a difference in the height between 2 points, not the distance between 2 points. अगर ऐसा एक streamline होगा तो इनके बीच का height क्या होगा, इनके बीच का height होगा dz. Okay, so essentially the height difference between two points, v is the velocity and dv is the change in velocity. This is known as the Euler's equation of motion of fluid flow. This is called the Euler's equation of motion of fluid flow. So it essentially connects the velocity, the acceleration due to gravity, the change in the particle's height in terms of the gravitational field, change in the pressure and the density of the fluid. Derivation समझ में आया? It was not difficult, lengthy, इसलिए I included it in the discussion.
Yes, sir.
All right, now shall I move ahead to the next topic?
Yes, sir.
One very simple consequence of this Euler's equation of motion is what is known as the Bernoulli's equation. Now there are various assumptions that I have not yet discussed too much in detail. We are discussing streamline motion, okay, steady state flow. And if we include a couple of more considerations, like if the fluid is incompressible, non-viscous, irrotational, etc., I can simplify this equation to give us what is known as the Bernoulli's equation. Okay, let me write it down separately. Which time I have? Yeah, I have sufficient time. So Bernoulli's equation, which is also very important. So Bernoulli's equation, as of course it is applied to incompressible fluids. The fluid must be steady and continuous. Non-viscous flow. Irrotational flow. Velocity is uniform in a cross section. Velocity is uniform in a cross section. Only gravity and pressure differences are concerned. Only gravity and pressure differences are considered.
Sir,
Yeah.
so can you please explain again this final equation, this Euler's equation, the terms involved there? I mean, this V will be at any point. So can you please explain again the terms here?
The rho, you understand, this is the density of the fluid. Yeah.
Yes, sir.
The dp basically tells us about the static pressure difference between any 2 points. So if you are trying to study the motion of a fluid between, let's suppose, point A and point B in the presence of gravity, then the velocity may go from v to v plus dv if there is an associated vertical displacement of dz and a pressure difference of, let's suppose, p and p plus dp, then all these quantities are connected by this equation. So let's suppose I know the static pressure difference, I know the acceleration due to gravity, I know the vertical displacement, I know the density, then I will be able to find out the changes in the velocity of the fluid.
Got it, sir. Thank you.
Yeah. So just like in Newton's law, if I know the force, then I can calculate the acceleration. I can see the change in velocity. Here, if I know the acceleration due to gravity, the pressure difference and the density, I can figure out the change in the velocity of the fluid in between 2 points. We'll do some questions related to this, don't worry, not today but tomorrow. So this will become a lot clearer. But there is one important consequence of the Euler's equation of motion that will be revealed by the Bernoulli's equation. So let's suppose I integrate the Euler's equation of motion, okay? Integrate the Euler's equation of motion. So if I integrate the Euler's equation of motion, so this is nothing but dp upon rho plus g dz plus v dv is equal to whatever integration of 0. So integration of 0 will done with respect to whatever quantity you do come out to be some kind of a constant. So let's suppose a constant c1. So in a very small interval, in a very small region, I can take the density because I'm saying incompressible fluids. So the density is constant, then the density is constant. And let's suppose the over a short period of flow change in the region or time, the pressure difference comes out to be, the integration of dp comes out to be p, which represents a static pressure difference. Then there will be some sort of a constant c2 if I do an integration, some constant, and g, and I'll have a z here. So z in some books they write it as h, okay, in some books they write it as x, maybe x like that, dz is equal to h. So h is nothing but h is the vertical height, okay, z is in the vertical direction, so h is the vertical height, okay. So h लिख देता हूँ मैं इसको, it's a vertical height plus some kind of a constant c2 plus v square upon 2 plus some kind of a constant c3 over c3, some kind of a c4 is equal to c1. If I take all the constants to the right hand side, I'll end up getting p upon rho plus gh plus v square upon 2 is equal to some constant C5, let's suppose. And because the density of the fluid is a constant, if I multiply with the density, I get P plus rho GH plus half rho V square is equal to some kind of a constant. This is the Bernoulli equation. The Bernoulli equation is essentially to deal with energy, all right? It basically is actually a conservation of energy, a restatement of the conservation of energy principle. What we have here is associated with the pressure energy or the static pressure energy, whatever, because of whatever system, whatever reasons the fluid is experiencing some sort of a pressure. So this is known as a static pressure that corresponds to pressure energy that some fluid is experiencing. This here rho GH is basically what? Gravitational pressure, okay? The pressure exerted due to gravity. Gravitational pressure that is exerted due to gravity, and this quantity is essentially the the dynamic pressure, which is a result of the kinetic energy of the particles. So everything is written in terms of pressure, but they correspond to the kinetic energy of 1 unit volume of fluid. So this is associated with the kinetic energy of, let's suppose, 1 unit volume of fluid. Okay, so essentially the Bernoulli's equation gives us an idea about the restatement in terms of the physical quantities that we deal with in fluid mechanics of the energy conservation. So energy conservation happens, and uska jo restatement hai can be written in terms of P plus rho GH plus half rho V square. So if I am comparing the motion of a fluid in a tube or a cylinder or in an object or in some sort of a cavity, and I have at two different locations, so therefore in two different locations where changes in the height, changes in velocity, changes in pressure takes place, I can simply write that this is equal to P1 plus rho 1g. I can say H1 or something like that, depends upon the height. 1g H1 plus half rho 1 V1 square is equal to P2 plus rho 2g H2 plus half rho 2 V2 square. Okay, so we will be using this formula in this particular form in various problems. So I have a lot of problems to discuss. How much time I have left? Achha, any questions you have till this point? There are some applications of the Bernoulli's theorem that I want to discuss, but it's going to take some time. So I just have 10 minutes. The applications I'll discuss tomorrow.
Sir, what is static pressure? Like static meaning?
This is the uniform pressure in between any 2 points that is not changing with time. Okay, it is not coming as a result of gravity. It is coming as a result of some other source. Maybe there is a pump that is creating some pressure difference in a pipe, or maybe there is anything, whatever it is, not necessarily due to changes in vertical displacement, but it is due to the configuration of the system itself, that there is a pressure between any 2 points. Okay, that static pressure essentially.
Okay, sir.
Not necessarily because of gravitational pressure, which is the second term. It is because of any other reason, maybe in the configuration of the fluid itself. Okay, let me give you one. Yeah.
सर जैसे बीच में शायद ने बताया था कि वो अपराइट पे प्रेशर कम होगा सर, वो बता दो क्या होता है, पता नहीं कैसे कम होगा.
प्रेशर यहाँ पे ज़्यादा है, यहाँ पे कम है, प्रेशर डिफरेंस है, इसलिए तो फोर्स एग्जिस्ट करता है ना. प्रेशर का मतलब क्या है? फोर्स अपॉन एरिया ना. फोर्स है इसलिए तो फ्लूइड मोशन है.
सर कहाँ कम और कहाँ ज्यादा है ये बताने के बाद.
जहाँ फ्लूइड जिस तरफ जा रहा है उधर प्रेशर कम है ना.
मतलब सर जहाँ P प्लस DP लिखा है वो कम है.
वो कम है, वो मैंने प्लस डीपी लिखा है तो माइनस साइन आ गया, बट वो बैलेंस हो गया अल्टीमेटली इक्वेशन में, डजंट मैटर. वो कम है, माइनस नहीं आता अगर मैं माइनस डीपी लिखता.
सर ये विजुलाइज नहीं कर पा रहा सर मैं नॉर्मली यहाँ कम होने का रीजन वैसे देखे मान के चले कि हम फिजिक्स के एस्पेक्ट में नहीं देख रहे वैसे देखे नॉर्मल प्रश्न के थ्रू
प्रेशर मतलब फोर्स इनटू एरिया, ठीक है। लेट्स सपोज यहाँ पे एक फ्लूइड है, आपने अपने हाथों से यहाँ पे कुछ फोर्स डाला हुआ है, ठीक है, और यहाँ पे कोई बंदा एक और फोर्स डाल रहा है, ठीक है। जिधर ज़्यादा फोर्स होगा मोशन तो उसी डायरेक्शन में होगा ना।
हाँ यस सर
जिधर ज़्यादा फोर्स होगा, ज़्यादा फोर्स मतलब प्रेशर इनटू एरिया।
हाँ सर आ गया सर समझ
ठीक है।
थैंक यू सर
मैं एक सवाल देता हूँ, आज ज़्यादा टाइम नहीं है। आई विल डिस्कस द एप्लीकेशन ऑफ बर्नौलीज इक्वेशन विच आर मेनी, देयर आर मेनी एप्लीकेशंस ऑफ बर्नौलीज इक्वेशन, आर वेरी इंटरेस्टिंग एप्लीकेशंस. So I need some time to discuss those applications, but I want to give, because I have some time, a very simple problem that you can try and tell me the answer based on one of the concepts that I've discussed in today's class. So please try this question. An ideal fluid is flowing. It's a very easy question. An ideal fluid is flowing through a tube of a cylinder of cross section or cylindrical cross section of varying radius. The velocity of fluid particles at one point where tube's cross section area is 1 into 10 to the power minus 4 meter square, is given by 0.01 meter per second. The velocity at a point where cross-sectional area is 2 into 10 to the power minus 4 meter square, is given by what? ठीक है, आपके ऑप्शंस में दे रहा हूँ, टेल मी द आंसर. इट्स अ वेरी इजी क्वेश्चन. Ignore gravity, no need to take into consideration gravity. So 0.0025 meter per second, 0.005 meter per second, 0.02 meter per second, and 0.04 meter per second. So this is a question that came in JAM Geophysics examination in 2006. An ideal fluid is flowing through a tube of cylindrical cross-section of varying radius. The velocity of the fluid particles at one point where tube's cross-section area is 1.1 into minus 4 meters square is given by 0.01 meter per second. The velocity at the point where cross-section is 2 into 10 to the power minus 4 meters square is given by what? Okay, Ankit correct answer, Sachin correct, Ramanan correct, Durgesh correct, Keshav correct, Neetu correct, Said correct. Good. Sandeep correct, Ayush, Jagdish correct answer. Yeah, कौन सा इक्वेशन लगना है इसमें? क्या बोलते हैं उसको?
Equation of continuity.
हाँ, तो कॉन्सेप्ट इज इक्वेशन ऑफ कॉन्टिन्यूटी. आइडियल फ्लूइड, आइडियल मतलब बेसिकली स्ट्रीमलाइंड है, एंड स्टेडी स्टेट, स्टेडी फ्लो. तो उसके लिए A1 V1 is equal to on incompressible A1 V1 is equal to A2 V2. तो essentially A1 है तुम्हारा 1 into 10 to the power minus 4 meter per second. V is given by 0.01. A2 is 2 into 10 to the power minus 4 meter square, sorry, and V2. Okay, so therefore ये तुम्हारा हो गया कैंसिल, हो गया कैंसिल, and V2 is therefore equal to 0.005 meter per second. This is your answer. Okay. Simple equation of continuity. So tomorrow I'll be discussing in greater depth applications of the Bernoulli equation and problem solving associated with Euler's as well as Bernoulli's equation, Bernoulli's theorem. ठीक है, आज के लिए इतना ही. It's almost 9.
Sir,
Yes, Jagdish.
sir, while studying fluid dynamics, what sort of physical parameters we encounter which can be termed as tensors, sir?
I'm not exactly sure right now. Tensorial
Sir,
quantity.
is pressure one of them?
Pressure. I'm not sure. It shouldn't be. Pressure shouldn't be a tensor, but I'll check upon it once. Okay, I'm not sure as of the moment.
Oh, okay.
I don't know why should pressure be a tensor. Pressure is essentially the force per unit area. Force is a vector. I can associate a vector quantity with every point in space and divided by area. It should not be, but I will confirm you tomorrow. Okay.
Okay, sir.
All right, guys, I'll discuss this topic further tomorrow and prepare for the test on Sunday. Okay. आप लोग का टेस्ट इतना ज़्यादा एक्सेलेंट नहीं हो रहा है, थोड़ा सा. दिस इज द लास्ट टेस्ट ऑफ मैकेनिक्स, सो प्रिपेयर इट वेल. आई विल सी यू टुमारो. हैव अ नाइस इवनिंग, गाइस. बाय बाय.
So the mathematics text will be on 21st.
The Sunday after this.
Okay, sir.
So possibly there will be 2 MP tests, Sunday after this as well as the Sunday after that. Okay. Chalo, bye bye, guys. Bye. Have a nice.
Thank you, sir. Good night.
All right.
Bye,
Good
sir.
night.